Welcome to Learning for Knowledge channel. Today in this video we will continue with the basic concepts of reverse osmosis and some more definition will be explained in this video. I hope you will enjoy and understand these terms. We are repeating the concept of this reverse osmosis. In this first A figure you can say this is the process of osmosis, and in the B figure there is osmotic equilibrium developed between these two compartments which are separated through a semi-permeable membrane, and in this third one, C part or C diagram, this is a reverse osmosis when we overcome this osmotic pressure and as well as resistance of the membrane. So this process is become reverse osmosis. Now basic terms, definitions related with the reverse osmosis we will continue in this. The next term is this limiting salt. Salt that reaches its saturation concentration first as water is concentrated in reverse osmosis system. There are different types of salts are present in the water, and they are, when the reverse osmosis process clean the water, the concentration of the salts increases on the reject or concentrate side. Among those salts, the salt which reaches its saturation, or you can say dissolution limit, then it starts coming out from the water and start precipitating. This is called limiting salt. Recovery or conversion is a term used to describe what volume percentage of influent water is recovered as permeate, which is basically a purified water. So for example, if normally RO system recoveries ranges from about 50 to 85%. Now a system recovery of 75% means that for every 100 gallon per minute influent, 75 gallon per minute will become permeate and 25 gallon per minute will be retained as concentrate. So recovery is calculated using the following equation. Percent recovery is equal to permeate flow divided by feed flow multiplied by 100. This gives the percent recovery of the influent water, and most of the system now working between 50% to 80% and depend on the influent chemistry as well as the pressure applied in this system. So at 75% recovery, as in the previous video I explained, the concentrate volume is if 1/4 that of the influent volume. What this means, if we assume that all the particles or the dissolved solids are retained at the membrane, then if the recovery is 75%, then concentrate will contain four times that of the influent stream. Yeah, the concentration increase 4 times. Or if the recovery is 50%, its concentration in the reject or concentrate is the doubled twice. So this is, as already explained, called the concentration factor. This diagram explains this phenomena. For example, this is this diagram shows concentrate and instantaneous permeate concentration as a function of recovery. We will start from this left side of the diagram, that when recovery is 0 and the feed concentration is 100 ppm, as this process going on, so when we get 50% of the recovery, the concentration of the dissolved solids become double, 200, and if it's working on the 98%, then the instantaneous permeate concentration is 4 ppm. And if at the 98% rejection membrane, if its recovery increase to 75%, then the feed concentration become 400 and only 8 ppm will be present in this permeate dissolved solid in permeate. So basically what is going on, as you can say the total volume is constant, so the salts which are retained or rejected through a membrane remain in the concentrate, and they are now increasing. This is called the concentration factor. This if you want to detail, then you can see the part 1 of this video. So after recovery there is a rejection. This is the formula journal. Rejection is 1 minus Cp over Cf, So rejection is a dimensionless quantity, and Cp concentration in permeate moles per liter and concentration in feed water moles per liter. So this is the rejection, or you can say rejection 1 minus this ratio. There is another important term, beta or concentration polarization. Beta is sometimes called concentration polarization factor, and it is the ratio of the concentration of species at the membrane surface to that in the bulk solution. The higher the beta number, the higher the relative concentration at the surface, because it is the ratio of the species at the membrane surface. If that's become higher, then the beta value become also higher. If the concentration at the surface gets high, then there will you can say there will be a performance problem arises in the RO membrane, and because due to high concentration at the surface, maybe some salt reach its limiting point, or saturation may be reached, and scale will start beginning and has a negative effect on the performance of RO membrane. Specifically, it reduces the throughput of the membrane. So therefore, higher the beta number, the more likely the membranes are to foul or scale. Maximum acceptable beta typically ranges from about 1 to 1.2 to minimize formation of scale. So ideally its value should be 1, that is the same concentration in bulk solution as well as at the surface of the membrane. So there will be no question arises of scale formation or depositions. Next term is fouling. So membrane fouling is a result of deposition of suspended or dissolved solids, organics or microbes on the surface of the membrane. A fouled membrane exhibits two major performance issues. Number 1, higher than normal operating pressure and higher than normal pressure drop. Why? This is due to the fact that foulants collect on the surface of the membrane, and they form an additional barrier layer to transport through the membrane. This diagram explains this phenomena. Now this is the membrane, and this black strip shows the surface fouled. Now because due to presence of this fouling, the holes of the membrane blocked. Now we need external pressure so that water can pass through these fouled surface. So that's why we need extra pressure, and the product or permeate, or you can say recovery also reduces due to fouling. So this phenomena must be considered during the operation or operating of the RO plant. Next important term is flux. The flux is defined as the volumetric flow rate of the fluid through a given membrane. This is normal thing, and flux basically is expressed as gallon of water, or you can say liter of water per square foot or per meter square of membrane area per day. The flux of water through an RO membrane is proportional to the net pressure driving force applied to the water. Next important thing is silt density index. This is basically a test, not the RO performance or RO related you can term. So silt density index is a test that measures the potential of an influent water to foul an RO membrane with suspended solids and colloids. Basically in this test, flow rate of the influent water through a 0.45 micron filter paper has been used, and the time of the flow, and also the you can say this colloidals or anything stopped on the surface of the filter paper are observed. Maybe in the next of our videos we will explain this silt density index test in detail. Next term is scaling. The scaling of RO membrane is a result of precipitation of saturated salt on the surface of the membrane. Now after these basic terms, we will explain the types of filtration processes involved in this RO scheme. There are two types of filtration. One is dead-end filtration and second is crossflow filtration. Number 1, dead-end filtration. So dead end filtration is also called end flow or direct flow. This diagram shows the process that we have membrane and there is only one stream which is influent stream. When it passes through this membrane, we get only one stream of effluent, and all the impurities will be stopped on this membrane. So this is the dead end filtration, and this is a batch process because after some time this membrane will be choked and we have to replace or wash this membrane. So that means that filter will accumulate and eventually blind off with particles such as the water, such that water can no longer pass through it. The filtration system will need to be taken offline and the filter will need to either be cleaned or replaced. This is dead end filtration. This is not common in the RO process. Next is cross-flow filtration. So in cross-flow filtration, feed water passes through tangentially over the membrane surface rather than perpendicular as in dead end filtration. So water and some dissolved solids passes through the membrane while the majority of the dissolved solid and some water does not pass through the membrane. Hence cross-flow filtration has one influent stream, that is we have water coming from one side but yields two effluent stream. One is called permeate and another is concentrate. This diagram basically shows the cross-flow filtration process. So here is a feed of the water. This is the membrane. So from this membrane water passes through and other remaining dissolved solid and concentrate stream goes from this side. So at the end we get two stream, clean water which is permeate and concentrate which is called reject. So with an applied pressure greater than osmotic pressure of the solution is separated into two effluent states. This is basically a reverse osmosis phenomena which similar to diagram shown in the beginning or in the previous video. The solution that passes through the membrane is called the permeate or product as I already described, and the solution retained by the membrane is called concentrate or reject. This is the cross flow filtration and this is used in the reverse osmosis process. This is another way of showing this cross flow filtration process. This line, this diagonal line is a semi-permeable membrane and feed comes, and from this feed, when this feed reaches to the membrane, water, pure water become separate and pass through this membrane and become permeate, and the remaining part which contain dissolved solids in concentrated form and some water, now it's come from this line which is called concentrate or reject. So this is another way of describing this. So these are basically two processes. This cross flow filtration process is a better process, and it seems that like in dead end filtration, which is a batch process, it is a continuous process. But after some time, when lot of solids and scaling and fouling happen on the surface of the membrane, we need to replace this membrane or change this and stop the plant. In the next video we will continue and describe this further membrane process, or you can say purification of the water from this. So I hope you will enjoy these lectures and continue to see these videos. See you in the coming videos. Thank you very much.